All right, here we go. This is, I think, my third time trying to do these notes. I'm going to try and see if we can get this. So we're going to open up to 214, and we'll be working with on the pyramid on 213. So you are going to go ahead and sort of open the book up so we have access to both pages. We'll go ahead and write down your essential question in the top. These are known as energy flow notes. That's the header on page 214. So I know it doesn't really match the title of the slide. So energy in an ecosystem. So the essential question, we should be able to answer this at the end of the notes. How does energy move or flow through an ecosystem? So that's going to be the question that we're going to answer. So yeah, so let's get going. You can write that down. You can pause the video so you can write down the notes. All right, so ecosystem, and I changed it up a little bit because I didn't like the word ecosystem in the definition of the word ecosystem. So it's all the biotic things and abiotic, the living things and non-living things in the defined space working together. So it could be as little as a defined space as this pond. It could be bigger, such as a desert, and it could even be bigger as the earth. So we can look at the biotic things in this picture. You can see the deer, the frog, the raccoon, the fish, the turtles, plants, all those different types of things. And the abiotic would be the water, not only the water, but let's say the temperature of the water, even, is it fresh water or is it salt water? And then we have the atmosphere, is it sunny all the time? Does it rain a lot? Is it warm? Is it cool? Those types of things would be abiotic. Okay, so all the biotic and abiotic things in a defined space, and you can sort of put a little arrow under the ecosystem, and that's what we mean, right? So defined space that are working together. All right. The first thing we're going to see is, where does all the energy come from that makes us live, right? So it comes from the sun. Most of it comes from the sun. 98% of all Earth energy on Earth comes from the sun. 2% comes from the hydrothermal vents in the ocean. It's sort of interesting. The other day I was watching this video on the Mariana Trench in the Atlantic, and so if you want to look that up, that's the 36,000 feet below, under this, it goes down 36,000 feet. And when you think of, like, let's say Mount Everest is the tallest mountain, it's about 19,000 feet. So it goes down a lot deeper than the Mount Everest is up. So those organisms on the very bottom of it, they don't have the sun to rely on. So where do they get their energy from? So there's these volcanoes underwater. That's what a hydrothermal vent is. And you have chemicals such as sulfur and such. And so they're called chemosynthetic organisms instead of that photosynthetic organisms. All right. So that's, so the next line, and I changed it up. Well, I didn't change it up. So I said the law of conservation of energy states that energy is not created or destroyed. It is only transferred from one organism to another. All right, so we talk about energy as it exists on Earth. Now you might think or know that, the sun is creating this energy that's coming down to Earth. So we're going to talk about energy as in the closed system of Earth. Once it reaches Earth, it comes into the plants, it is, from there, it's only transferred to one organism to another. So we're talking about the enclosed Earth. We talk about the first law of thermodynamics. And that word that's interchangeable with the conservation of energy. So the first law of thermodynamics states that energy cannot be created or destroyed. So those two statements are interchangeable. When we say the first law of thermodynamics, we are talking about the conservation of energy. All right, so the next we're going to talk about trophic levels. I'm trying to think. Okay, so and we'll talk about trophic in a second. So organisms are organized based on their type of consumption, what they eat or where they get their energy from. Whoops, I'm trying to move this around. So the levels are going to be called trophic levels. And when we're talking about consumption, we're talking about nutrition, right? So that's what trophic means. In Latin, it translates to nutrition for the most part. And so we look at this, what we're going to call a consumption pyramid or an energy pyramid. We organize those levels in this period. And that's where we're going to go ahead and work with page 213, since that triangle is already drawn for you. So the first level are the producers, and these are the plants. These are the things that convert the sun into sugars. If you've ever remember photosynthesis, we have carbon dioxide and water, and it turns it into oxygen and glucose, and that glucose is the sugar. Now, when we talk about energy within a molecule, we're talking about the bonds that make up the molecules. You know, if we have a carbon and that has a hydrogen bond to it, that bond is where that energy is stored. And so when those bonds are broken, energy is released. All right, so we have producers. They're also known as autotrophs. Auto meaning self, troph meaning nutrition, right? So self-nutrition, right? So they make their own nutrition. They make their own sugars. And they are in, I don't know why it says topic level. Maybe I need to change that. It should say trophic level number 1. Trophic level. I'll go ahead and change that when we're done here. So the sugars that are produced by the producers is going to support all the organisms above it. And we're going to see how that works. So now we're going to talk about, whoops, I don't know what happened. The primary consumers. These are the things that eat, or the organisms that eat the producers. All right, they're called heterotrophs. Hetero meaning different. So they need to get their sugars or the nutrition by eating something else. All right, and those are in the second trophic level number 2. All consumers are considered heterotrophs. So everything above the autotrophs are going to be heterotrophs, meaning they get their energy from consuming the sugar molecules from producers. All right. I think I mentioned photosynthesis, but that was one of the words that you needed to write down. All right, so next is secondary consumers. Now these could be carnivores, but they could be omnivores too, and I didn't change that. So an omnivore is something that eats both the plants and animals. Carnivores only eat animals. So a secondary consumer is something that can either eat the primary consumer or a producer. So if you think of, let's say, bears reside in this category because they can eat herbivores, they can eat fish and things like that, but they can also eat berries, right? So they can eat both. So they're not only carnivores, they can be carnivores. So like, for instance, this organism here, I think that's a fox that just eats meat, right? It doesn't eat plants. So it could be either a carnivore or an omnivore. So that's OMNI and then vores, okay? Again, heterotrophs. Tertiary, so this is, tertiary means third level, so third level consumers. They are in the 4th trophic level. These are usually the top predators, right? The carnivores, right? So they only eat the secondary consumers. So these are usually just meat eaters, right? Again, you can see that they're heterotrophs. Again, they get their energy from consuming any other animals, right? So they only eat animals. So if you think of, let's say, a mountain lion or a lion or an eagle, they're only going to eat animals, organisms underneath it. All right, so we're done with that portion of the pyramid, but however, we have these things called decomposers. So these don't really reside within the triangle themselves, because they're going to decompose anything that is dead, right? So that could be a plant, that could be a ladybug, and it could be a lion, right? So their job is to break down all the dead matter so it can be recycled back into the soil, right? So, I talked about how we can all have atoms from, organisms thousands of years ago or millions of years ago. And this is why, because those decomposers put it back into the soil. Now, one thing that we're not mentioning is like scavengers, right? So like, vultures or something like that, that actually, they actually get their energy from dead things, usually animals. They don't usually eat dead plants, but they do eat dead. And that's just a pure nutritional source. All right. If you think about Venus flytraps, those are producers still. They dissolve the insects just to get nutrition. They don't get it to make energy. All right. All right, so now we're going to go switch to 215, and we're going to keep on talking about I think I missed this slide. So now we're going to talk about energy and how it flows through through this pyramid. So as you can see with the energy, the arrows, the energy only flows one way. It goes up through the energy level. The arrow is only going one way. Only 10% of that energy from an organism moves up from one trophic level to another, right? So it says the first bullet point is a triangle is used because not all the energy moves from one trophic level to the next, right? Only 10% of it gets passed on. So if we have 10,000 calories or kilocalories available for the producers, only 1,000 of that will be available for the consumers. Only 100 kilocalories will be available for the secondary consumers, and so on. So 10%, all right? So you just take off a zero. All right, so based on the first law of thermodynamics, we tell you that energy is not created nor destroyed. So, energy is still there. So where does that other 90% go? Well, if you think about it, we need energy to survive. So some of that goes into metabolism, right, keeping us alive. I'm gonna, the major portion is it's lost as heat, right? So that's the majority of it is, just lost as heat. Chemical reactions produce heat, and it just goes ahead and goes into gets dispersed into the atmosphere. Also, if you look at it, there's no way that all of the primary consumers will eat all the producers, right? That wouldn't make sense, right? And then, we would just have everything gone, and then we wouldn't have anything to continue on. So there's a lot left over, right? So that's why only 10% is left. So the second law of thermodynamics, we talked about the first law. The second law is that loss of heat, meaning that, okay, we had this 10,000 kilocalories, but how come, we only have 1,000 kilocalories available? Well, all this energy that is lost, we can't reuse it. We can reuse this 1,000 kilocalories because it's in the form of sugars, and we can break those chemical bonds and get that energy out of it. But this heat, once it dissipates into the atmosphere, we can't reuse it, right? We can't use that energy to, keep us going, right? We can't capture that energy again. So that's what we mean by decrease in quality, all right? So sugars are high quality sugar, right? Because we can use them, but the heat is low quality. We can't use it. And that's what we mean by the second law of thermodynamics. All right, the next is biomass. So biomass is the total mass, so think, trees, if we have these trees in our ecosystem of organisms in a given area, right? And I don't know why I have this, because it's not necessarily the amount of organisms in an area, because if you think about it, think about the trees that we have and how many insects are within those trees. So we're going to have a lot more insects than we are going to have trees, all right? But it's the mass. So, but mass wise, we have a lot more trees than anything else. So, we might have, 100 million kilograms of trees, all right, in this park, but there's no way that we have that much mass of the primary consumers, right? The insects and the birds and things like that. There's no way that there's going to be that much mass in with that primary, in the primary consumers. So how does that work? So, and I'll have to change this. So how does that work? So again, let's say we're just talking about this tree and it weighs 1,000 kilograms, which is probably way too much, but that's okay. Regardless of how many insects, ants, and birds and caterpillars or whatever else is feeding off this tree, it's going to be nowhere near this mass. All right, even like an ant weighs, you can see what that is. I don't know, the 3 times 10 to the -6 kilograms, right? So that's really, really light. And how many ants will you need to have to meet that mass of trees? There's no way that there's going to be that many ants, you know. But if you take up all the insects and the birds and the other things, the grasses, right, it's going to be more than a mule deer combined, right? So we might have, I don't know, maybe 1,000 kilograms um, of insects and birds and things, but the mule deer, the things that feed off the grasses, will be a lot less. All right, so you can see how the biomass decreases as you go up the energy pyramid, and that's what this is showing here. All right, so the pyramid, you can see all the leaves right here. I'll sort of move that out of the way. So, we have a lot of leaves, we have less insects, less birds, and then less hawks. All right, so yeah, so we have the biomass decreases as you go up. All right, so here's another example. I'll move this over here, sort of get this out of the way. Since energy is lost at so we're at the biomass pyramid, right, the bottom. So you should answer the question, well, explain why biomass is used instead of number of organisms. And I think I explained that. All right, biomass pyramid. Since energy is lost at every level, the amount of organisms at each level will decrease as well, right? So there's going to be less primary consumers than producers, and there's going to be less secondary consumers as primary consumers, and there's going to be less tertiary consumers as secondary consumers, and so on and so forth. And we sort of went over that. If you think about it, let's say if you go to a park, or you're in the hills here, right? There's a lot of grasses, and you might going to see some birds, a lot of birds, and other things, and then you might see some snakes. You might see some secondary consumers, 1 or 2 snakes, and then you're going to see maybe some rabbits, and then you're not going to see very many mountain lions, right? Because so there's not enough secondary consumers to support very many mountain lions, right? So I think the range of a mountain lion is like 7 to 8 miles. So there's only enough energy to support maybe 1 or 2 mountain lions in a particular area, just due to the fact that there's not very many secondary consumers that they can feed off of. So, as you get higher in the energy pyramid, the less organisms you're going to have. And it's mass, right? We do talk about mass, and we don't necessarily talk about number of organisms. All right, so that is the end of my slides. All right, so that's it. And we'll continue this. We'll see you in class.